What I thought I would do is talk about network processors, since there may not be that many network processor guys in the audience. And the summary is it's pretty much the same as other multi-core processors, except that there's differences. Network processors we have a very embarrassing parallel problem. A lot of the packets can be treated completely independently, and packets keep coming in, so you can do huge amounts of parallelism if you want to go fast. Consequently, current network processors often have a lot of cores. 32 to 256 are pretty common numbers in the current generation. There's stuff surrounding them. There's a lot of very specialized packet processing stuff that goes on. That tends to fall into two camps. There's lookups, and there's things you have to do to the data path. I'll talk a little bit more about those up here shortly, I think. Yeah. So here's the problem to be solved. A packet comes in, and the most important thing you have to do is decide where it's going to go out of this particular box that you're in. One could argue that that's the only thing you have to do, and there's a tremendous number of boxes in your network that do nothing but that. Those tend to have ASICs in them because it's a very simple, or not simple, it's a constrained problem to take the header out of a packet and figure out what the destination address is and figure out which port you should send it out of your box. So typically you don't have an NPU in that kind of box. That's a very cost-sensitive market. You just send stuff. That's a very big market. It's much bigger than the NPU market. There's a lot of those things out there. But you just bring it in, you do a lookup. Sometimes the lookups are a little bit tricky. There's wildcards. There's various lengths of lookups. There's lots of different kind of packets you have to handle, but it's relatively straightforward and often in an ASIC. So why do you have NPUs? You have NPUs because often there's a lot more stuff that people want to do than just bring the packet in and send it out. I won't go into all the details of that for the sake of lunch. The main thing that you want to do, though, that there's stuff in an NPU to do is a packet comes in. Packets are typically very big compared to the header. The header is often 32, 64 bytes. The packet is often up to 1,500 bytes. Often an NPU will take those and stick them into two separate memory spaces. The last thing you want to do is take a sort of a generic multiprocessor sort of structure and bring the whole packet in, which flushes everything out of your caches with the data part of the packet that then you don't really necessarily do anything with. So often that's separated and very carefully controlled. Just the buffer management, because the packets are coming in at like 150 million packets a second or so in a normal single Ethernet port. You often have hardware to do your free lists and your buffer management just because you don't want to spend your software cycles to do something that you do so frequently, and that's a relatively straightforward thing to do. You'd often do a number of different kinds of lookups in a network processor-based box. You often look up the destination for security. Sometimes there's some translation involved. There's a bunch of different protocols you might have to look up. So usually an NPU will have accelerators in it for the various kinds of lookups that you do as well. I said often that the payload comes in and you don't do anything with it. Often you don't, but there are specific cases where you do. You will find at the edge of your network a lot of times people do encryption or decryption to do like VPNs or various security things. The opposite of that is actually DPI, is what we call a deep packet inspection, where you actually look into the packet to see what's going on. That actually sounds sort of like snooping on people, and it's used for that, but it's actually used for more useful things to normal people, like firewalling or protecting you from viruses, or in some cases even things are aggregated into bigger streams and you have to look inside to do the right thing in your network to make it happen. The NPUs will often have queuing structures because a very fundamental thing in networking is queues. Packets come in, you put them in queues. It's quite important usually that you keep order. In theory, in the networks, the end stations are supposed to be able to reorder their packets if they get slightly out of order in the network, but that's not guaranteed to work all the time, so it's usually considered bad form to reorder the packets as they go through. Plenty of systems have bad form. Often what they try and do is not do it in any way that anybody ever actually notices. And then, so often there's a really big block actually on the thing that then once you've queued up all of these packets, called a TM or a scheduler is basically what it is, that selects which queue to send out. And there's a whole Actually, okay, I'll tell a small story even though we're totally out of time. You know, if you buy, I assume it works the same here as it does in the States where I'm from, which is you go to your internet service provider and you say, you know, I want to buy 10 megabit DSL to my house or something. And you would think that this would give you 10 megabits. But the scheduler in the last box before your house has this fancy thing, because a bunch of your neighbors are also attached to that thing. And when you buy 10 megabits, actually what they're doing is they're capping you at 10 megabits so that you never get more than 10 megabits. You might have thought that you'd be getting 10 megabits, but actually when you pay for 10, that guarantees you never can get more than 10. And the scheduler is actually quite complicated because you and your neighbors are massively oversubscribed. So if you all paid for 10 and you all wanted 10, you can't all have it. And so there's certain amounts of fairness and stuff. So often this is actually a quite complicated block in these things. And the most important thing that sells network processors is actually people often want to bill their customers for their packets going through. So it used to be network processors started in like 98, 97, 1999, something like that. The very first ones often were kind of quirky state machine microcontroller-like things that were not very programmable. Often they were programmed, well, often the companies went out of business, but the ones that succeeded were either easier to program or the companies themselves had programmers that would program them for their customers to do the function that they wanted. I talked mostly about all of these functions already. In fact, I talked about most everything on this slide already. Nowadays, however, most of them use RISC CPUs and don't have strange or custom things with special purpose instructions. And that's largely because of programmer productivity. Maybe 15 years ago, it was useful to optimize to try. In fact, I built some that was actually somewhat successful. You could go faster if you didn't have a full-blown CPU. Nowadays, the chips are big enough that you're not going to survive in the market, basically, if you don't make the programmers productive instead of just send the packets through faster. So basically, everybody is already at or migrating towards multi-core RISC CPUs. And as I said, they got 32 or 256 of them. Previously, they often used a bus or a point-to-point or actually crossbars for a certain amount of scale were very popular, but NOx, because crossbars are running out of gas already at the size we're having, is becoming a much more complicated thing. And, okay, I put this bullet on even though I knew it wouldn't be news to anybody here, which is power is a big problem. So the networking software guys have two ways that they program these things. One is called run to completion. Almost everything happens when a packet comes in and starts execution. So run to completion means a packet goes to a specific thread or a specific core in your NPU, and it does its entire execution there. And then it finishes. So it owns that thread. This has some nice actual secondary properties for making the software easy to write. You get sort of an implied lock. Some of the NPUs will send everything from a specific flow that has to stay in order through a specific thread, which means all of the flow particular state can only be accessed by that thread, and therefore you get an implied lock because all of the packets from that flow will go through that thread. So you don't have to use locking. You don't have to worry about ordering because everything will just queue up waiting for that one thread. You don't try and fan it out and put it back together in order. That's about half, it seems like, in the industry of how people are using these things is in a run-to-completion model. The other one is unfortunately named software pipelining because when I was doing CPUs a long time ago, we had already used software pipelining to mean something different. But in network processor context, what they mean is the computation that the packet goes through is divided into phases, and a phase is locked to a thread or a core. Sometimes it's allowed to move around. The more important part is phases, and usually it's locked. And so you will take the context of a packet and you will move it from core 0 when it's done with phase 0, for example, to core 1 to do phase 1, to core 2 to do phase 2. And in that way, you form a pipeline of the phases across the different threads or the cores. That's probably about the other half, I would say, on the whole, of how people use these things. It used to be that cache coherence was non-existent on NPUs because it's not that easy to get it to work fast. It's not that easy to get it to work at scale. And NPUs were often built by networking guys and not processor guys, and they didn't really know how to do it. Nowadays, almost everybody has it. Not everybody, but almost everybody has it, and the reason is, again, to make the programmers more productive, because you can go find any programmer you want straight out of college, and they know how to program something that has a flat, uniform memory system, because that's how programming models of the system exist. It's not completely necessary for this application scenario. A lot of the stuff is not shared, and that's why it used to be that way. But now you find that basically almost all network processors have cache coherence entirely to simplify the programming model. It also used to be that most of them, just for speed, didn't run an OS on the multicores. They ran it bare metal. Nowadays, I think you'd find that maybe it's 75% of them will run an OS. There's still a certain fraction that are just performance critical, where you don't want to take the overhead of the OS. But for the rest of them, again, it's ease of programming. Ease of programming is everything in terms of successful deployments. At the high end, right now, we're talking about 100 gigabits per second. Networking guys talk in bits and not in bytes. It took me a while to get used to that. The interesting data points, just as generic rules of thumb, is I already mentioned that you can't send the packets just into your cache system, because you'll just totally thrash out all the useful stuff like the headers and the lookup tables and the accounting statistics. One bullet that I didn't put on the slide is if you just take a look at forwarding packets on a general RISC processor. I did this analysis myself a couple of years ago and was rather shocked with the result. The question is, if an average packet is, say, 200 bytes in size, which an average packet is, and you do everything just in software, then how many instructions do you fetch to forward data? And the answer was you fetch an instruction, and amortized, you have forwarded a bit of data. So for every bit you want to forward, if you do everything in software, you have to fetch an instruction. Well, you can imagine what this does to your power budget, because you fetched a 32-bit instruction and decoded it and executed it, and on average you only managed to forward 1 bit out of your 200 gigabits per second. This is why you end up with even more hardware accelerators over time. And then because of all of these tables, the 6x is actually almost entirely memory bandwidth for table lookups. The header lookups are not completely trivial, especially for IP, because they have a hierarchy in the lookup. And that adds up. In fact, that's becoming a rather critical problem. We're right at a juncture where you can't go off-chip with enough bandwidth, and you can't quite fit enough on-chip for the size that you need. So we're at a very awkward moment right now. I think in a couple of years we'll be able to fit all we need on-chip, and people are struggling. So this is a beautiful diagram that I stole off the Cavium website from their marketing department, I'm sure, that demonstrates some of the things that I've just told you. I don't know if you can read those from where you are. They use 48 MIPS cores, although I believe they've announced that they're switching to ARM. But the current generation all uses MIPS. They still use a crossbar for their interconnect. They have coherent caches. It actually runs an operating system. And then over here on the left-hand side, we have in the light gray is sort of I/O, and then in the blue is the various accelerators. Don't know that this necessarily is in any way proportional to the actual area on the die, although it's somewhat in the right neighborhood for what I might expect it to be like. So here's the chip I built for Huawei. Now, we don't actually sell this outside of Huawei, so I apologize for the fact that I don't have such a glossy marketing diagram. This is based on an engineering presentation. But you can see that we have some of the same things. We have, this is definitely not proportional to die area. Up there in the upper left, we have processors. We have it surrounding a NOC because our scale is much higher, so we don't have a very fancy NOC, but we certainly don't have a crossbar in the middle of our chip. There's a lot of memory, DDR in this case, attached to the device, And then there's a lot of, SM stands for smart memory. That's basically memory with accelerators. Most of the accelerators in network processors have to do with memory operations of some form, if they're not just things like crypto or stuff that just operates directly on the path. And then down here on the bottom, okay, over here on the left, we have I/O. Packets come in. They often go through some input queues in most of these things. And then here on our chip is the data path accelerators. This is the block that I said, the TM, traffic manager, that's often really quite large. When I started doing networking back around 99, that was when traffic management was starting to get popular, and nobody really knew how to do it. Our customers would all say, actually they'd call it QoS, quality of service, but really that's just traffic management. And we'd say, do you want QoS? And they'd say, yes. And we'd say, what do you want? And they'd say, we don't know. And so there was a lot of churn around here. And I have to tell you that in my mind, even the current state of the art there is, it's sort of become standardized. So everybody has expectations of what it can do for you. And if it can do that, then the customers are happy. So unfortunately, I think we're likely to stay in that sad state for quite a while because the customers don't know it's sad. So in summary, we actually do tend to put a lot of cores on NPUs compared to some other multi-core things because we have this really, really highly parallel problem. In fact, for a lot of applications, it's somewhat arbitrarily parallel. If I didn't run out of power, I could put on more cores and use them because I could just suck up another 1,000 packets if I needed to fill up another 1,000 cores. Nowadays, NOC is common for scalable. OS and coherence, I would say, are just about to become requirements from a market perspective unless somebody has a better way to just throw new college grad programmers onto these things and have them be able to use them. And then really everything above the line is common for multi-core network processors. The stuff that makes it a network processor is actually the stuff below the line. That's where the secret sauce, if there is any, is what kind of accelerators do you need? What kind of balance do you have? How do they talk to each other? How do you deal with the lookups and the high memory bandwidth requirements? So it's mostly the same, but there are these little tricky differences that sort of miraculously define a whole new market if you put these little accelerators on your chip. That's all I had. There's one.
I'm Hollis, University of Bristol. I was very interested by this comment about the memory throttling, what you can do now. So you're saying there is not enough off-chip bandwidth, but yet you can't build enough on-chip memory.
Yeah.
And you're suggesting that in the future this will sort itself out. But I might assume that as you solve this, you'll just build a bigger system to process more data, and this comes back again. So do you see this long-term throttling what you can do?
So the memory bandwidth mostly goes to the tables.
Right.
And the tables are growing in size, but they're not proportional to bandwidth. They're more proportional to the size of the network, which, of course, continues to grow. And so 15 years ago, you pretty much had to be able to store 500,000 routing table entries to be a big router. Nowadays, 15 years later, if you have like 2 million, you can easily contain the current tables. People might not buy that because they've been sort of trained to need more. But you could be operating with something that had 2 or 3 or 4 million for the next 8 or 9 years. And so that, if you compress it carefully, will fit on the chip the next 10 years worth of table. If you had, say, 10 megabytes of on-chip memory, which you can do now. You could do that now. So if you took your next generation one and you, say, allocated 20 megabytes of memory for on-chip lookup tables, that will exceed the growth in table size for the next 10 years easily.
And that will still be true with the Internet of Things putting routable devices everywhere?
Yeah, so there's two kinds of lookups. There's flat, which is what Internet of Things will be, and then there's hierarchical. The Internet is hierarchical because it couldn't be flat. But localized, you could be flat. So you have to switch to hierarchical as soon as you get big enough. So if Internet of Things means all the things in my house on the Internet, then yes, obviously that's not going to be a number in the tens of thousands. I can fit that on a chip. If Internet of Things means every refrigerator and washing machine and toaster in England, then we probably have a problem. So the hierarchy of Internet of Things will have to stop at some point in terms of global visibility. But that already all works, right? It's just a question of are you layer 2 or layer 3 addressable.
That's very interesting. Thank you very much. Thank you.